Okay, in this podcast we're going to talk about how to do titrations and how to do the calculations for them. And then the second podcast actually shows you physically how to do the titration and the techniques that are involved. Okay, so a titration is used to find the concentration of some solution or some sample that you have that you don't know what the concentration is. So when we're doing a titration, we generally have some substance that we know its concentration, and we call that the titrant. And then the analyte is the thing that we are analyzing, and that is the thing we are trying to figure out the concentration of. And when we're doing a titration, we use a setup that looks just like this. This is a burette, and if you look at a burette, if you were to blow that up, you would see that 0 is up here and 50 is down here. So you're reading it the opposite way than you would a graduated cylinder. And if you look further, you will see that there are lines for the 0.1 milliliters. So you should be reporting your volumes to 2 decimal places. Okay, so you should be estimating between the 10th lines. So you might get 0.15. Okay, so you need to report 2 decimal places on these. Okay, so the thing that we are trying to figure out generally goes in the flask underneath the burette. That's the analyte. The titrant is the thing that we have the concentration for, and we're using that to help us figure out what the concentration is. So a lot of words here about cleaning the burette. Believe it or not, these questions do show up on the AP exam, and the most important thing with cleaning the burette is that you must have your last rinse of the burette be with the substance you are using in the burette. So if you were to rinse it really, really well with distilled water, and then you did your titration, you would end up diluting the solution of known concentration when you put it in there, and it can mess up your results. So depending on if the burettes have been used before you, if someone has done the same titration before you, you can simply rinse it with the substance that you're using. If you're just taking the burette off a burette stand that has been sitting around for some time, you should start with distilled water rinse, and then always end up with rinsing twice with the solution that you're titrating with. Okay. The other important point, and this says actually people have lost points for not including it when asked how a burette needs to be prepared. The other thing is when you have your burette, and you fill it up between the stopcock and the tip, you might be filled with air. So you always have to make sure you run some through and make sure there is no air in the tip, that it should be filled completely with solution. Okay, so you can read this through. Bring it with you to the lab to make sure you are using the right procedure for preparing your burette. Here again are information about how to actually fill the burette, and you should be following this. You will see this demonstrated for you in the video that's to follow, but you want to make sure you have these notes for your lab. Okay, so this is quantitative analysis, so we have to be very precise, and one of the things that can happen during a titration is a drop comes off the burette and it might actually hit the side of the beaker. So one of the things we want to be doing is constantly rinsing the inside of the flask with distilled water to make sure that we have every drop of the titrant that is in that flask, even if it's on the side. Okay, and as it turns out, adding additional water does not affect your calculations, because if you had to, let's say, determined that you have a certain number of grams or moles of some substance in here, that's what you're putting in there, right? So you're measuring it out, you're massing it, you're using a solution of it, and that is what you're going to use in your calculation. And then you add water to it, and that additional water does not get used to recalculate the molarity. You're using the original molarity of what you put in, or the original grams of what you put in. So don't worry about adding water, it won't affect your calculations. Okay, when we're titrating an acid with a base, we are almost always using phenolphthalein as our indicator. and the indicator will turn pink when it has reached basic. And so what we're looking for, so initially nothing will happen. You'll have a clear solution because your acid will be clear, and you'll start to see pink that is lasting, and then you slow down on the stopcock. What you're looking for is the palest pink that stays, let's say, for 20 to 30 seconds without disappearing. It could actually disappear and become clear. That means you need another drop. If you get a big bright pink, that means you've gone too far. Now, it's not unusual for that to happen, especially on your first titration, and you can use those results, but make sure you are very precise with your next ones. Okay, so when we see that pink, that is a visual indication known as the end point. It means that we have actually, in reality, gone one drop beyond our equivalence point. Our equivalence point in an acid-base titration is when the moles of acid equal the moles of base. Okay? And the way phenolphthalein works is it turns pink when it becomes a basic solution. Okay? So that you want your endpoint, the point you stop at, to be very, very close to your equivalence point, which is why you need to slow things down. Okay, so your endpoint or your equivalence point is when your moles of acid equals your moles of base. Your endpoint is when you get the visual cue that that has happened or you've gone just past it. In order to figure out the concentration of an unknown, we can use stoichiometry, factor label, or you can also use a titration equation. And what you want to know is that your moles of acid equals your moles of base. It's really your moles of H plus equals your moles of OH minus. And because we know molarity times volume is equal to moles, we're using something very similar to the dilution formula. So this is the acid, this is the base. There's one more little bit of a complication. If you have NaOH, that has one OH for every 1 mole of this. If you have, let's say, H2SO4, then you have 2 H pluses, okay? So what you need to do is make an adjustment. You need the number of hydrogens for your acid, and you need the number of hydroxides in the formula for your base. Okay. All right, so here's a problem. We have, and actually, let's go back before we do that and talk about what's happening during the titration. So if I have, let's say, a weak acid, let's say I had HF, and I'm titrating it with sodium hydroxide. As it turns out, that is not an equilibrium reaction. It's not a reversible reaction. It is a one-way neutralization reaction. And what I always get during a neutralization reaction is a salt neutralization reaction. I get a salt, in this case would be NaF, plus water. Okay? It's not an equilibrium. And it goes all the way to the right. So even though HF is weak and sodium hydroxide is strong, the HF ends up completely ionizing. Because what's happening is, let's say you're adding a drop of OH to this HF, and there's enough HF here that it's going to neutralize it and become water. And then the next drop comes and you have more HF that's available. So it's this continual process of your shifting things to the right. It's really based on the Chatelier. So you want to know that you always end up with a salt, be able to write those equations. Okay, so let's do a problem. So let's take a look. We have 25 milliliters of 0.1037 molar HClO. It's titrated with sodium hydroxide. We need 12.72 molar of the hydroxide to reach the end point, and we want to know the molarity of the hydroxide solution. This is very similar to what we'll be doing in the lab to standardize the NaOH. So the first thing we want to do is write the equation. So I have HClO plus sodium hydroxide, and what you always end up with is the H here and the OH here ends up becoming your water, and then you end up with a salt of what's left. In this case, it's NaClO. So if I apply my neutralization formula times the number of H pluses equals my molarity of my base times the volume of my base times the number of OH minuses, right? Now in this problem we have one H, so that's going to be 1, and we have one OH, so that's going to be 1. So I'm trying to find the molarity of my base, so it's going to equal the molarity of my acid times the volume of my acid over the volume of my base. And in this case it's going to be molarity of my acid is 0.1037. The volume of my acid is 25.00 milliliters. And I can do the same thing here. As long as my units are the same, I can use any volume units. And I'm going to divide that by 12.72 milliliters of sodium hydroxide. And you see these units will cancel. And if I do that and plug it into my calculator, I get a molarity of my NaOH is going to be 0.20. Let's see, we have 4 sig figs, 4 sig figs, 4 sig figs. So we want 4 sig figs here. Alright, let's do one more. Here we have sodium hydroxide in the flask, 10 milliliters. This is concentration. We're titrating it with sulfuric acid solution. And we want to know the molarity. So let's write the equation first. So I have sodium hydroxide plus H2SO4. And I'm going to make water. And I'm going to make sodium sulfate. Sulfate is a -2 ion, sodium's a +1, so I need 2. So I'm going to need 2 of these, and I end up with 2 of these. So recognize that I've got 2 hydroxides for every one sulfate here in order to get moles of acid equal moles of base. So my moles of acid times the volume of my acid times the number of hydrogens is going to equal the molarity of my base, the volume of my base times the number of hydroxides. My molarity of my acid is what I'm solving for, so that's going to equal molarity of the base, volume of the base, number of hydroxides, over volume of my acid. And that will be molarity of the base is 0.1037. My volume is 10 milliliters. I'm putting that over the volume of the acid, 12.72. Now, what I missed here is I need the number of hydrogens down here. That would have been a mistake if I hadn't done that. And what I have is 2 hydrogens in sulfuric acid, so that's times 2. And if I plug and chug, I end up with a molarity of my acid of 0.03898 molar H2SO4. All right, we're going to stop right there. Watch the next podcast, which shows you how to do the physical titration.